Alright guys, welcome to today's class. We're still gonna go over 3D geometric nettings and figures. So let's get started. Alright, let's do example 14. The figure shown can be folded into the shape of a cube. In the resulting cube, which of the letter faces is the opposite, the face marked by X? Well, how do we approach this? Well, first, notice that this, we can just make an entire cube out of this, right? Say this is this bottommost cube. Right over here, that's B. We want to make this netting. Right over here. We want to make this netting. Alright, so what do we do? So basically, how do we do this? Well, from here, we can imagine ourselves making this netting. Or we can make an actual netting with paper. You draw out this figure. You fold these figures, fold it into itself, and you will see it happen. Like, fold the edges. This example folds over here, and then we can fold this way, over here. We can also fold from here to here, which then just connects it to fold this edge to that edge. And then you can see where this E goes. Alright? From there, if we fold it all out, you'll see that E is on the top. And I encourage you to try it out on a piece of paper. Draw the figure, label the squares, and then fold. Alright? So in this case, the answer is just E. Alright? Now let's move on to example 15. Find the other vertices that meet with vertex 1 when the resulting net is folded. Same exact thing as we do here. We fold the figure. This one's a much more complicated figure this time. In this case, the figure here is, I think it is an octahedron. Yep, it's an octahedron. Why? Because in an octahedron, there's 8 faces. 8 triangular faces. In this case, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 faces right there. From here, we notice that, well, if there's 8 faces, we know how to fold this, right? We pull, we try to find a center, in this case, find a center. Alright? But there's also a cool trick. There's a really cool trick. If we want to see, if we have vertices right over here, I want to find which vertices be with vertex 1. Well, one way to do this is step 1, draw a line across 2 triangular faces. Step 2, find other points that are the same distance to point O. In this case, you can see there's 1 and 2. And then in step 3, conclude that vertices 1, 2, 3 will meet each other when the net is folded. That's the trick. Alright? It's a pretty cool trick. And in this case, from here, you'll notice that this vertex and that vertex meet with vertex 1. Right? Now let's move on to problem 7. The length of an edge of each of the 6 cubes in the solid is 2 centimeters. In square centimeters, what is the total surface area of the solid? So let's have a try on this question and tell me as if you chat. All right, guys, let's get started with this question. So, problem 7. The length of an edge of each of the 6 cubes in the solid is 2 centimeters. All right, we get that. So, we can label every edge to be 2 centimeters. In square centimeters, what is the total surface area? All right, how do we approach this from here? Well, notice that we first can count the front, this entire front edge. We will break it into parts. Count this, then the bottom, and then these two sides, which are the same, and then the back. From here, if we count just this part, alright? If we count this entire stair, basic like shape, the square's area is 4, since 2 times 2 is 4. Alright? What else? Well, since this is 2 times 2 is 4, we can label each area of this square is 4. Well, how many squares are there in total? In this case, on this side, right over here, on this side, entire side, that comes out to be 1, 2, 3, 4, 5, 6, 7, 8. There's 8 squares, right? So let's just count the squares, since much easier to handle than multiplying. We can just find the total number of squares, then multiply it by 4 to get the total surface area. In this case, how many squares are on the side now? Since the sides are the exact same, these are the exact same, that's 4, 4, 4. That's 3 squares with the area of 4. And notice that there's 3 on the other side too, since they're the exact same. Now, what about the back? What do we do for the back? The back has four squares. How do I know? Because the length of this is 2 squares, and the height of this is 2 squares also. You can easily translate this into 2 squares. The side length is not 2, it's just the square's length is 2. I mean, the amount of squares there is 2. So there's 4 squares. Similarly, we can use this argument to see that there's 2 squares on the bottom. From there, we've counted all the faces. There's 1, 2, 3, 4, 5 we took care about, and there's a total of 5 numbers. We add this all up, get 11 plus 3 plus 8, which is just 22. But we're not done yet. Since we only found the number of squares, and we know that each edge in each of the 6 cubes is 2 centimeters. This is telling you that the area of each square is 4 centimeters, since 2 times 2 is equal to 4, as we talked about before. And then from there, we include this in, get 22 times 4 is 88, or B. Alright? Now let's do problem 8. The following polyhedron with dimensions as given has a value of 7 cubic units. How many faces does the figure contain? 3 edges and 1 vertex of the polyhedron are not shown in the diagram. Alright? Let's have a try on this question in 10 minutes to chat and private message. All right, guys, let's get started with this question. So basically, how do we do this question? Well, notice that we first have to draw the polyhedron since there are three edges and one vertex that are not shown in this diagram, which means the back, right? It's not like we're missing any edges in the photo. So basically, what we do from here is note that how many faces the diagram contain. In this case, how do we count it? Well, each of these is considered one face, right? Make sure that you don't say, "Oh, this is an entire face." No. All right. So from here we just count. There's one, two, three on the third is on the bottom, four is on the other side, five is on the back. So we basically counted everything over here. Now we'll move on to these small faces. Now there is 5, 6, 7, 8, 9, 10, and 11. Make sure to count that. Or did we already count that? You gotta make sure that you don't accidentally overcount. And in this case, we did count this already. So we make sure to subtract 1 because we already counted it. So 11 minus 1 is 10. So the answer is C. So make sure, in most of the counting problems, make sure you don't overcount or undercount. Make sure if you're overcounting, then subtract the ones that you overcounted on. Undercount, add some stuff that you undercounted on. And then from there, you're basically it. So you counted correctly. In this case, we got 10, and our answer is just C. Alright? Now let's do problem 9. The drawing shows a solid made of stacked cubes. Which of the following best represents the base plan for the solid? Let's take a try on this question and tell me through chat in private message. All right, guys, let's get started with this question. So, what do we do? So basically, notice that first there's two. This is one, this is one, this is one. This is three, since we just count the basically, if you guys don't know what a base plan is, the base plan is basically meaning that if we draw a base diagram, we first look at the base, and then we tell you how many cubes are stacked on one part. Okay? So in this case, this part has two cubes stacked. So we write a 2 over there. Similarly, this is one cube stacked, so we write a 1 there. And continue that for the entire base. From here, we can do by guessing, check, and elimination. We get 2, 1, 1, 1. And we get 2, 1, 1. It's either one of these two, since there's 4 on the bottom over here. Now we check the second row. It's 3, 3, 2, 1. Let's see if it follows that. 3, 3, 2, 1. 3, 2, 2, 1. And from there, we know that A is the right answer. Alright, let's do problem 10 now. Draw a solid object that corresponds to the following base plan. I'll let you guys have a try on this question in 10 minutes to chat. Alright, guys. Sorry about whoever's using a pink color and scribbling all over the screen. But anyways, Eva drawed pretty good right over here. Right over here, she drawed pretty good. And that is a brilliant demonstration of a base plan, and you use it to draw a solid object. All right. So if you guys didn't see it, I'll I'll draw it over here. Well, it's over the screen, but whatever. But if you can see Eva's was brilliant. I think if I can direct onto it properly, if I can, yeah, it's over here. This one is a really great demonstration, and probably draws better than me. I'm not gonna be lying over here. But anyways, that is a perfect solid object with a base plan. Not a perfect, but it's really good. All right. Now let's move on to problem 11. This time we'll have to draw a base plan for this following object. All right. I was gonna have a try this question and tell me answers through chat. You can annotate on this, but don't. Whatever. Go ahead. All right, so if you see all these drawings that have been check marked, they're all correct, except with that question mark, because I don't know what the figure is on about. But whatever. So basically, how do we approach this question? All right, how do we approach this? Well, first off, you know the base plan over here. That's one. All right, since there's only one cube above. Second one, there's one, two, three. There's three over here. That's 3, 2, 1. All right, as we talked about before. And then finally, we get over here is 4. This one's 3. This one's 2, and this one's 1. It goes down this pattern. And there's the single. All right. So now let's move on. Let's move on now to problem 12. The piece of paper can be folded up to form a cube. What numbered face will be the opposite of the number 6 face? Let's give it a try on this question and tell me your answers through chat. All right, guys, let's get started with this question. In this case, we let 3 be the center. All right. So we can fall forward to get 4. And this is, since we fold it back, the opposite of 4 is 2. This case, you can get this one's 5, and this one's right over there is 1, 6. So basically, it's just folded. This case, the opposite is just going to be 3. So the answer to this question is just C or 3. Example 16. It's 2004 Marathon State Sprint number 21. This net is folded into regular octahedron. What is the sum of the numbers on the triangular faces sharing an edge with the face with a 1 on it? I was going to try on this question and tell me to through chat. By the way, you guys can annotate on there. Just so you know, you guys can draw on the screen if you want, if it helps you visualize better. Alright guys, same exact method as we did before. Basically what we do is basically note that with the one with it, one on it, do 1, 4, and like this. This gets you get 1, 4, and 8 together. And then, but we have a 2 over here. And then 2 also shares an edge right over here. So from there, you get the answer is 4 plus 2 plus 8, which is equal to 14. So the answer is just 14. Alright, now let's move on to problem 17. Example 17. The net below can be folded to form an octahedron. When it is folded up, which two vertices are glued to vertex V? Let's take a try on this question and tell me this through chat. All right, guys, let's get started with this question. All right, guys, no more talking. Let's get started with this question. All right, so we do the exact same method as we did before. All right, we draw a diagonal straight as we did before, to find which of them intersect. In this case, that's 1, I, H, V. Since V and H and I are together, it's just telling you the two vertices are H and I or high. All right, now let's move on to example 18. If the strip of triangles as shown below is folded to form an octahedron, and each vertex is assigned the value of the sum of the four triangular faces which it belongs, find the minimum value of a vertex. I'll take us have a try on this question and 10 minutes to chat. Alright, guys, let's get started with this question. If the strip of triangles shown below is folded to form an octahedron, and each vertex is assigned the value of the sum of the four triangle faces to which it belongs to, find the minimum value of the vertex. Well, how do we do this? We first draw the diagonals that we've drawn before. Alright? In this case, we can do this. That'll be what all that's left is going to be 1, 2, 4, and 5. Or we can do it like this. Because this gives you 1, 2, 4, 5, the minimum. Alright? This is from there, just casework. You just do this diagonal, then this diagonal. Let's please not. Let's please not do that. Alright? So from here, you can just draw the diagonals. And then notice that these are the ones that connect like this. So from there, what we do is notice that the minimum value from here is just going to be 1 plus 2 plus 4 plus 5 This is just going to be equal to 12, or the answer to this question is just 12. Right? Now let's move on to Euler's formula. This one's a really, really great formula. I recommend you to know how to do it and memorize this. Alright, so from this question, Euler's formula is f plus v, faces plus vertices is equal to edges plus 2. And the edges and faces formula is edges is equal to faces times sides divided by 2. Right? Now let's do example 19. The diagram shown is the net of a regular dodecahedron. In a dodecahedron, 3 edges come together at each vertex. When the net of this dodecahedron is put together, the solid has x vertices and y edges. What is the value of x plus y? Alright, let's get to the try on this question and tell me this to chat. Alright guys, let's get started with this question. So basically, how do we approach this? Well, notice from here, if we draw it out, it's going to look like 12, there's going to be 12 pentagons. I'm not going to draw it that accurate. I hope you get the point. You can just search up the figure, what a pentagon looks like. It looks somewhere like this. Alright? Something like this. Alright? From here, you can see there's 5 vertices on the pentagon. If we were to look at the figure, which I cannot draw perfectly, and I cannot draw it very good. If you were to draw it out, or look at, made up just off a picture, you will see that there's 5 on the very top. 5, actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pretty sure 10 on the middle. You can count again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there's 10. And the bottom has another 5. And then you can count the edges. There is 4 plus 4 plus 4. Well, in this case, how many edges are there? Well, we first know find the vertices, which is actually 20. Edges are 30. Just we can see over here. And then faces are 12. You can just do the calculations. And from here, get faces times the size in each face. 12, it's just 12 times 5. 60 divided by 2 is 30. Easily get the edges using this formula. And get 30 plus 20 is 50. It's that simple. Alright? So that's it for today's class. I hope you guys have a wonderful weekend. I'll see you next week. Bye.